Fossil fuels won't last eternally. Hence, we need to come up with an efficient way of generating renewable energy for the future. This was our mission. More specifically, we were tasked with designing a horizontal axis wind turbine with the highest possible efficiency. The requirement for this project were the following. The tip speed ratio, defined as the tip speed divided by the wind speed, had to lie between 3 and 8. The maximum RPM had to be below 3000. The wind turbine had to be manufactured as one piece and had to be 3D printed inside a box of dimensions 400 by 150 by 75 millimeters. After careful consideration, it was decided that the turbine should be one-bladed with a hinge in the middle in order to maximize its size. Here is our thought process.
The ultimate design choice was between a one-bladed and a two-bladed turbine. One-bladed turbines are more aerodynamically efficient, but increased risks are involved, such as the hinge and the counterweight. In a two-bladed turbine, the blades are spinning much closer to the preceding blades, meaning that the effects of the wake are much more significant. In real life, one-bladed turbines tend to lead to the most cost-effective designs. The best way to summarize the one-bladed design choice is that there is a high risk for a high reward. When looking at wind turbines for industrial applications, they are almost always three-bladed. The reason for this comes not from efficiency, but from the requirements for mechanical and dynamic stability. The two main reasons are as follows. For most large-scale wind turbines, they are mounted atop a large tower. This tower causes stagnation of the flow in front of it. As the blade passes across the tower support, the pressure across the blade decreases, causing a decrease in moment about the horizontal axis parallel to the blade. This effect is most significant for one- and two-bladed turbines. Since the blades pass periodically in front of the tower, this causes periodic oscillations, which, in the worst-case scenario, could cause catastrophic failure. For our tests, there will not be a tower which stagnates the flow, thus these effects will be minor. Another main problem with both one- and two-bladed turbines is that, should the wind direction change slightly, the effect of the change in angle of attack of the blade would be more significant for one- and two-bladed turbines. As before, this causes oscillations, which could cause failure. Since the flow direction is fixed for our tests, this will not present an issue for us.
In order to select the airfoil, Sadiq and Gugar's research paper, new airfoils for small horizontal axis wind turbines was used. The SG6043 airfoil was selected for the base due to structural considerations. In addition, the SG6040 airfoil was chosen at the tip since it had the best lift-to-drag ratio at low Reynolds numbers. Moreover, the chord was not kept constant along the blade, since for optimal performance, the circulation should be uniform. Furthermore, with increasing radius, the peripheral velocity increases, causing the angle of incoming flow seen by the blade to decrease. In order to ensure the airfoils experience the optimal angle of attack, the blade must be twisted to account for this. Thus, the chord and pitch of the airfoil sections were calculated using Schmidt theory. By recollecting actuated disk theory, the theoretical maximum CP which can be obtained is 0.593. This is known as the Betz limit. The blade was then modeled in Q-blade in order to check its performance. At a wind speed of 12 meters per second, Q-blade predicted a maximum power output of 160 watts at 800 RPM.
The main two forces we considered acting on the beam were the centrifugal forces acting at the root of the blade and the lift and drag forces acting along the blade. Other forces such as the torsional moments along the blade could have also been considered, but due to the insignificance of these effects compared to the aforementioned effects, we decided against it. Starting with the centrifugal force, we used numerical integration theorems to evaluate the cross-sections along the beam, and use this to calculate the centre of mass. We then evaluated the centripetal forces using this equation, which turned out to be 950 newtons, giving us a root stress of 5.56 megapascals, which was 20 megapascals lower than the yield strength of our material, which was really good. With regards to the lift and drag forces, we used simple bending theory, assuming no twist in the blade, and integrated over the beam to get the forces, moments, and deflections. We initially got a deflection of around about 120 meters, but after some careful consideration, we realized that this was quite a bit higher than we were expecting. As a result, we went back to our code, debugged it a little bit, and got a deflection of 6 centimeters.
Once the design characteristics had been determined, the first step from idea to finished product was to create a model in a CAD software. For this project, we had to use Creo Parametric. After a CAD model had been created, the files were sent off to the workshop to be printed using a 3D printer. While the blades were being printed, we also had to manufacture the hub. The general hub design had already been decided, and the only modification we made was to add an M10 threaded hole for the counterweight. This was then manufactured using a combination of milling, drilling, turning, using a 4-axis CNC machine. Once the blade had been printed, the process of creating a smooth surface began. The main tandem force experienced by the turbine is aerodynamic drag. A large part of this is made up of skin friction drag, so by having a smooth surface you can drastically reduce drag and increase blade performance. The last part of manufacturing the blade was to attach and balance the counterweight. This was done by screwing the M10 rod into the hub and adding washers while balancing it on a pin. The rod was then glued in place to avoid it flying out, causing lethal damage.
The final counterweight design was a result of the minimum moment needed to be created in order to balance the wind turbine properly. Initially, we pondered the idea of making an extrusion on the opposite side of the blade, filling it with washers, and then sealing it shut with epoxy. As this design did not yield a sufficient moment, we decided to extend the lever arm upon which the weight of the washers and nuts act on two axes, one being parallel to the blade and the other perpendicular. Lever arms were two steel rods which were fitted into extrusions. The rods were screwed into the hub and then were secured to the ABS plastic with epoxy adhesive. This resulted in a sufficient moment, but the trade-off was increased drag. To maximize the length of our turbine blade, we decided to include a hinge on the surface of the blade. This meant it was crucial to ensure that the design was structurally sound.
Do you want to close up Maurice?
Drop it. Yeah.
Let's talk about the results. The tests were carried out in the Donald Campbell wind tunnel, as can be seen here, and the tests were carried out at wind speeds of 6, 8, 10, and 12 meters per second, except we didn't manage to get past 6. Past 6 meters per second we got resonance in the blade, and it was unsafe to carry out the tests in such a small turbine. You can see a graph of the results here. We started down here and we slowed down the blade to extract power from the flow. We finally got a value of CP of... Yeah, Nicholas.
Oh, hey Nathan.
Hey, have you seen the CP? Yeah, what's up with that?
Yeah, so we got a CP of 1.06, but that's clearly unreasonable because we both exceeded the BETS limit and also created a perpetual motion field. These results can be explained by blockage. The decrease in CP seen from the RPM less than 1100 is most likely due to the onset of stall. When a turbine spins at high speeds, it acts almost as a solid disk blocking the flow. In a free environment, this effect is not too big, but in a wind tunnel, this could make a large difference in malus. The energy in the flow is equivalent to that of a higher wind speed, but due to the blockage, the measured wind speed at the start of the test is much lower. When the test begins, the turbine slows down because of applied brakes, and the solidity of the disk area decreases. As such, the flow speed increases. Because of this, the wind tunnel is typically picked so as to decrease the ratio of the turbine disk to the wind tunnel area. However, due to the large diameter of our wind turbine compared to the wind tunnel, our effect due to blockage are quite large. Because of the higher energy in the flow, our power output is much higher than it should have been at 60 meters per second. Had the blockage not been so significant, we would expect to see a significantly lower power generated and therefore lower CP. Also, the TSR would probably be lower since the flow velocity and thus the lift produced by the blades would be lower.
Right, blockage. Thank you. One thing we didn't consider when designing our blade was balancing the blade in the perpendicular axis. We did in the parallel axis and thus had a counterweight, but for the perpendicular we had to screw in an additional weight. As such, at higher velocities we got some crack propagation near the new weight. Something else we also could have improved in our turbine was to reduce the length of the cord at the root. Schmidt theory predicts a large cord at the root, however this creates a lot of drag and only really aids self-starting, and due to low peripheral velocity doesn't generate much lift. As such, we could try and make it smaller as long as the stresses in this area aren't too high.